Get started. Good morning, good afternoon, and good evening, everyone. Thanks, Peter, for the invitation, and thanks, Samuel, for the organization. It's my great pleasure to present our recent work on the flow seminar. My name is Honglin Yuan. I am a PhD student from Stanford University, advised by my advisor, Tengyu Ma. This work was done during my research internship at Google this past summer. This is a joint work with my collaborator at Google, Manzil Zahir and Sashank Reddy. I would like to thank Zach, Andrew, Ethan, and the TensorFlow Federated group for the help discussions. In this work, we propose a new optimization problem in federated learning, namely the federated composite optimization. The background is that the standard federated learning algorithms, such as federated averaging, are primarily geared towards smooth unconstrained problems. In this work, we studied a setting where the objective function includes a non-smooth, possibly non-finite additive composite term. We studied various algorithms to tackle this problem and discuss the theoretical complexity and empirical performance. Please feel free to raise your hand if you have any questions. I'm happy to answer a question on the go. Before we get started, let us briefly review how federated learning works. I think most of the audience of the flow are familiar with the motivation of federated learning, so I will quickly go over this slide to provide some basic context of this work. In federated learning, a pool of clients collaboratively train the shared model under the central orchestration server without disclosing their private data. The clients are usually like mobile or IoT devices with limited computation powers, but can also be larger entities such as organizations in the cross-silo federated settings. A typical federated learning process involves a series of rounds. At each round, the server sends an initialization to the client. The clients perform local training for a certain number of steps with their local training data and send the updates back to the server. The server then synchronizes the updates and broadcasts back to the client. The benefit of federated learning includes like better privacy guarantee, improves communication efficiency, and allows massive contributions. If we replace this framework, if we instantiate the local training step with some SGD steps, then this framework becomes the federated averaging, also known as local SGD. The federated averaging is the de facto standard algorithms to solve the unconstrained and smooth problem in federated learning. In this work, we follow a slightly more generalized formulation of federated averaging, which decompose the client learning rate into eta C, which we decompose the learning rate into the eta client and eta server. As you can see, that the federated averaging takes three hyperparameters: the initialization W0, eta client, and eta server. This formulation has been adopted in a series of recent work, such as Karimi Reddy's from SAML 20 and Reddy from I think it's an archive paper. But they both studied this slightly more generalized formulation of federated averaging. The main difference here is that at the server stage, instead of direct averaging this, they are taking a server gradient step based on the updates of the client round. This gives a slightly more generality compared to the simply averaging the client states. We list the pseudocode here for clarity. As you can see, the blue box are client updates, which performs SGD steps. At each step, it just takes, it queries a gradient and then updates this. This is just SGD steps. And after this round, the server will collect all the deltas of the client updates and treat this as a pseudo anti-gradient. The server then updates with the server learning rate eta server. If we take eta server to be 1, then this reduces to the classic local SGD or federated averaging. In this work, we consider a slightly more general formulation of federated learning. Recall that existing FL algorithms such as federated averaging solves this unconstrained smooth problem as follows. The objective is an average of Fm, where Fm is expected loss of the mth client. Dm, on the other hand, is a distribution of the mth client. We typically assume that Fm has to be smooth in order to derive a meaningful convergence rate for this problem. In this, we'll consider the federated composite optimization, where the objectives include the possibly non-smooth, non-finite additive psi-m here. The psi-m is called as convex composite functions. I will explain this in a moment. This composite optimization problem originates in a large amount of literature. We'll introduce some potential applications that are particularly interested in the federated setting. One of the most notable like the examples of this psi-m is to take psi-m as the regularizers. For example, if you take psi to be the L1 regularizers, then it reduces to the so-called lasso problem, where the goal is to retrieve sparse representations. This can be used in the FL setting. For example, if you consider the problem of a cross-silo biomedical FL applications, where several medical organizations collaboratively train a global model on their patients' data, but due to like privacy constraints, they cannot share their patients' data. In such medical applications, it's usually the case that the data amount is much smaller than the number of attributes or the features. So that the sparsity constraints are very important for the doctors and for the researchers to recover the meaningful signals behind this problem. And this can also be used to do a feature selection and other purpose. Another potential regularizer is the nuclear norm for matrix completions, where the nuclear norm is the summations of the singular values of the matrix W. Here, the W has to be a matrix, a square matrix for the nuclear norm to be applied. This nuclear norm will promote a low rank solution of W. There are other choices of the regularizer like TV semi-norm and LP norm, but I will mostly focus on these two setups for the experimental part. Another potential applications are the constraints, where the psi-m, recall that our main objective is the summation of the main objective FM plus a convex plus a composite psi-m. If we take this psi-m to be the convex indicator, which is defined as it is 0 if the W is in some convex set C, or plus infinity if this is not. Then it immediately reduces to this constraint problem, where the goal is to fulfill all the constraints if you treat this psi-m to be the indicators, because otherwise, if it's not in the constraint, then objective would be plus infinity. So it's equivalent to this constraint problem. This problem also has a broad range of applications. Here we list a few. For example, we can consider budgeting problem. If you want to sell a portfolio, it's like if you want to sell advertisements to a range of customers, but each customer has a budget constraint. Then at this setting, this problem becomes a constraint problem, where each customer has a personalized constraint. Other settings, such as monotonic constraints, can improve the interpretability of the problem. I'm happy I'm happy if you can input more applications for this part. Okay, before I move forward, any questions on the setup of this problem? Cool. So recall that in the previous slides, we proposed this federated composite optimization in the most generic setup, which is the summation of min objective FM plus a non-smooth composite psi-m. There are a few specifications that can simplify or specify the problems to somewhat simplify the hardness of this problem. One of the notable simplifications is the homogeneity versus heterogeneity of the objective FM. This is so-called the standard heterogeneity or non-IID-ness of the FL. This problem people have observed that the heterogeneity makes FL harder, both empirically and theoretically. There's a great line of work on identifying and overcoming the heterogeneity, such as Lee et al. From MLSys. This is also known as FedProx. Karimi Reddy, also known as the scaffold, and Woodworth, who studies the hardness of the local SGD in the heterogeneous setting. I think all of the 3 authors have present in the flow seminar. So if you are interested, please just check out the archive section of the flow talk to watch their wonderful talks. Another specification for our problem, which is kind of special to this work, is the consistency of the psi-m here. This is to see whether you want all the clients to have the same regularizers or not. This can have potential implications. For example, if you want to set a personalized constraints, then you should allow that each client has a different constraint. But for a generalization purpose or sparsity purpose, then this heterogeneity might not sound like necessary for the study of this problem. Another specification which is kind of interesting is whether you grant access to the composite oracle to the clients or servers or both. This is like whether you want the client to access this composite oracle. The implications here is that if you allow the client to perform with respect to this oracle, then you might have better convergence because you can see this oracle, you can see this composite for multiple times during this local training. And it may also lead to some privacy improvements because these personalized constraints need not to be shared to the server, like to this orchestration server. On the other hand, if you grant servers to this access to this oracle, then it might reduce the computational load on the client side because for certain composite oracle psi-m, this computation can be somewhat intense. We'll get back to this later. In this work, we focus on the slightly simplification of our previous proposed FCO problem, because we assume that the psi-m are homogeneous, but we allow for heterogeneous Fm. So this formulation will be the main objective throughout this talk, where the goal is more like to optimize the regularizer rather than the personalized constraints. So in the next part of the talk, we will discuss the potential algorithm to solve this problem. Before we get started, let us briefly review how to solve a composite optimization problem in the sequential centralized settings. So consider this sequential problem minimize f plus psi, where f is smooth, which we also assume to be convex, as you will see later, and psi is simple and convex. By simple, we mean that you can easily query this proximal operators with respect to this psi. So this proximal gradient descent is one of the most notable algorithms to solve this composite problem, f plus psi. The main motivation or the intuition here is that after doing a gradient descent step, which is Wt minus eta green f, then you do a proximal steps on top of this, which gives the following definitions. So this is one of the most famous algorithms to solve this proximal gradient method. This is more efficient than, say, other simple optimizer subgradients if you look at the rate for the centralized problem. There are 4 terms in this argument subproblem. The first 2 correspond to the first order Taylor expansion of f. The third term corresponds to the smoothest estimation because eta is usually taken to be 1 over L, where L is the smoothness. So if you replace eta with 1 over L, this immediately becomes the upper bound of this f. And psi is the proximal additive. So note that since f psi is non-smooth, we just leave psi as it is. But the key idea here is that it's usually the case that this subproblem can be solved usually analytically or quite or in a non-expensive way. For example, let's say that if you take this psi to be the convex characteristics, then it's immediately reduced to the projected gradient descent, where the algorithm looks like it first the gradient step and then project back to a convex set. If you have a projection oracle to the convex set, then this problem can be easily solved. Another notable examples includes like with decay, if you take psi to be a L2 square regularizers, and self-thresholding if you take the psi to be like the L1 norm regularizations. So this algorithm is also known to be the self-thresholding or forward-backward splitting based on the fields it appears. Okay, so now we have a simple attempt to combine the Federated averaging with the proximal gradient descent. The idea is quite simple. You just replace all the gradient descent step with a proximal gradient descent step. This will definitely, for example, if the psi is a constraint, then by doing this, you are always projecting back to the constraint. So you're always feasible. And under certain assumptions, you can show that this actually converges. But does it solve all the questions? So I want to make a quick note on the terminologies here. So despite sharing the same terminology prox, because we call this proximal gradient descent, this method is fundamentally different from the so-called Fed prox. In the Fed prox, the proximal step was introduced to regularize the client drift caused by the client heterogeneity. But in our work, the proximal step is to handle the additive composite term psi. So the problem approached by the two methods are also different because FedProx still solves the unconstrained smooth problem, but ours concerns with a composite term here. So here comes question: does this simple algorithm solve all the questions of composite optimizations? The answer is not really. We can identify a key challenge both theoretically and empirically. The major challenge here is that the averaging step and the proximal steps are somewhat discord, which mathematically it's because these proximal operations might be nonlinear, and therefore the averaging and the proximal operators do not necessarily commute. So here we have a simple intuition that why this the simple federated projected gradient descent might not work for some of the problem. So this is a simple intuition here. Suppose you have a point cloud around a constraint as a corner. If you first do a projection and then average, the point will be inside the corner. On the other hand, starting from the same set of points, if you first do an average and then do a projection, then you will end up inside. You end up on the boundary of the corner. So intuitively, we prefer the second scenarios because it gives a sharper solution. For example, if you are solving an I1 regularization, then it's likely that you have a sparser solution here. From a theoretical perspective, the second scenario is more desired because this is more akin to a large batch, mini batch. It's like you do a gradient descent step with an average gradient and then project. But unfortunately, we can show that the previous simple fix where the projected gradient descent step is embedded into Federated averaging. If you did this, then it corresponds to the first scenario, where it actually corresponds to your first projection and then average. This is a quick, simple intuition on whether the Fed proximal gradient descent step might not be an ideal choice for this problem. I'd like to pause here to take questions if there is any.
I don't see anything in the chat.
Okay.
Let me check whether anybody has a raised hand. I don't see anybody.
Okay, I'll move forward. So before we come up with a solution to fix the aforementioned problems, let us look a bit deeper into the proximal gradient descent step. Recall that this prox GD takes the following form. At each step, you solve this subproblem where you add a Euclidean proximal terms to this upper bound estimations. We can replace this Euclidean proximal terms with an arbitrary Bregman divergence induced so-called distance. This should be a distance because it's not actually a distance, which looks at the following. Instead of solving a Euclidean augmented term, you solve a Bregman divergence augmented term. So as we know that if we replace this HW with a square norm, where this norm is L2 norm, then it immediately reduces to the proximal gradient step. This method is known as the Bregman proximal gradient descent, which is also known as a Composite mirror descent or simply mirror descent hereafter. The benefits of this generic setup is that it enables the primal dual interpretation. The step from WT to WT plus 1 can be decomposed to the following 3 steps. At the beginning, you start from this primal WT. You map this to the dual space with this gradient H, where the gradient H is the map from the primal to the dual space. And then you add a gradient descent step to the ZT, where the gradient is evaluated at WT. This is the second step. And the third step is to map this back to the primal space by this inverse operators, where the star stands for the convex conjugate. This additional interpretation will be of important use when we figure out our main algorithm for this problem. Similarly, we can just quickly replace this proximal gradient step with a mirror descent step, but this does not solve the problem. This just gives us slightly more general formulations. As you see, we still call this algorithm 2 because it's just a slightly more general case of federated proximal gradient descent. Okay, so now we are ready to get into the main part of this talk. So another common algorithm to solve a sequential composite problem is the dual averaging problem. Recall that the primal dual interpretation of the mirror descent. You have to map the primal point to the mirror point to a dual space. You do a gradient descent step, and then you map it back. The key idea for this alternative algorithm is known as the dual averaging, is that instead of mapping forward and backward, we only map backward. So here's the intuition. So you can see that there's no forward mapping step. There's only a backward mapping steps. And you can interpret it as 2 steps. You start from a dual Z, at time t, you start from this dual state ZT. You map it back to the WT. You query the gradient at WT, and then you add it back to this ZT. So as you see that there's a persistent dual state for this algorithm. And this allows us to solve most of theoretical challenges. And as we will see that this corresponds to the so-called second scenario, the better scenario that we are looking for, if you recall this intuition of the corner cases. So here's a diagram. You start from the dual state ZT, you map it back, and you add it back to the ZT plus 1. So this ZT plus 1, ZT plus 2 is somewhat like more straightforward, and this significantly simplifies the problem. And as we will see, that it also improves empirical performance. This is also known as lazy mirror descent. If you see this this icon, so it's like you just reduce this forward mirror step. And I think that's the reason that people call it lazy mirror descent. And the reason people call it dual averaging is because this ZT can be considered as a average of all the gradients you have encountered, because you always add this gradient to the same Z. This problem has been I would say it's been discovered by Nesterov from 2009, but there are more work preceding this work from other fields like the online learning. And we follow the formulation of the Flammarion by Flammarion from Klaus 2017. A quick comparison between the mirror descent and dual averaging. In mirror descent, there's a forward and backward mirror, and we keep a persistent primal state. You can also interpret that as keeping a persistent dual state, but I would say that primal states entails a better understanding of this problem. And for the dual averaging, there's only a backward mirror. There's no forward mirror. There's no blue, and there's no these blue arrows. And it also it keeps a persistent dual state. That's the main difference between the mirror descent and dual averaging. Now we are ready to present our main algorithm, federated dual averaging. Compared with federated averaging, there are 2 main differences here. The first difference is that each client runs an instance of dual averaging instead of stochastic gradient descent, because you have to account for the proximal part. The second, which is the main difference, is that during the communication, instead of sending the primal states W, you are sending the dual states Z to this orchestration server. And these dual states are averaged and broadcasted back to another round of clients. So after communication, this orchestration server just sends this dual initialization to the second round of states, second round of clients. And because this is possible because the dual states are persistent. You can continue the commutation starting from this initialization of the dual states. And this gives our federated dual averaging algorithm. For clarity, we also listed our pseudocode for the federated dual averaging. Most of parts are similar to federated averaging, but I will highlight the difference here. This blue box contains all the client updates, which is simply the dual averaging step. At each step, you have to query the primal state and then add the gradient of this primal state to this dual state. This is exactly what we have shown for the sequential dual averaging. At the server stage, you have to average all the client dual deltas instead of primal deltas, and you add all these dual changes to this client dual state, ZR. This is optional step. This WR plus 1 is optional. It's only necessary if you want to output some intermediate results. For example, if you want to evaluate like training loss during this computation, you might want to compute the WR plus 1. But for the algorithmic purpose, this is not necessary to compute this point. So a quick summary of the comparison between the federated mirror descent, aka federated proximal gradient descent, versus federated dual averaging. In the federated mirror descent, we have to average primal because the primal are the main state. That you see that this primal are sent to the orchestration server. And theoretically, this is quite challenging, which is exactly due to the challenge we have just discussed, the nonlinearity of the mirror map, or the incommutability between the mirror map and the averaging operations. The fed dual averaging averages dual on the other hand, and it enjoys a nice theoretical interpretation via the dual shadow sequence. We'll get back to this later from a quick proof sketch. And of course, this outperforms fed mirror descent empirically, and that is one of the main contributions of this work. Cool. Before I move to the theoretical part, are there any questions? Okay, so now I would like to discuss the theoretical part of this work. Again, we are considering this slightly simplified cases of the federated composite problem where the psi is taken to be the same ones. We assume the following assumptions. So just a quick summary. The first two assumptions are standard regularity assumptions. For example, we need the convexity of F, the convexity of psi, and also like closeness and other regularity conditions for the psi. Since we have to deal with this Bregman-induced Bregman-induced divergence, we have to assume that H should be a right function to generate this distance, which is known as the Lagrange function, that is one strongly convex. This is somewhat standard in the study of the composite optimization problem. The assumption 1C assumes that the smooth the F each you can consider as each instance, or the thing under the expectation is also closed convex function that is smooth. This is standard in the analysis of federated averaging and other algorithms in federated learning. We assume that each gradient, each instance has sigma squared boundary variance under this dual norm within this domain. This is also standard, which assumes the boundary variance assumption. This assumption E is mostly which is mostly optional, I should say, but we assume this mostly for the ease of presentation of this work, because we can show that all the results we are going to show can be extended to the partial participation cases. Cool. Now we are going to show the first theorem on this work. This is in somewhat a simpler theorem, which we can show that in the small eta client, regime, both fat mirror descent and fat dual averaging can match the mini batch rate. Here, the mini batch rate, I means that it's R steps of MK batch. So it has a large batch, but the fewer steps, only because, as I said, that it's only the number of rounds of steps. So the result looks as following. As you can see, this LB over R corresponds to the deterministic convergence. Because you only have R step, this decays rather slowly. But this variance are inevitable because this corresponds to the hardness of the stochasticity of this problem. Note that this theorem only assumes the blanket assumption we just assumed, and it applies to both fat mirror descent and fat dual averaging. The reason that this result holds for both fat mirror descent and fat dual averaging is because in the mini batch cases, both two algorithms have the same rate. But as we will see that we will have a slightly, actually a stronger result for fat dual averaging in certain cases. Now we are going to show a slightly stronger guarantee for Federated dual averaging. We assume, yes.
I'll ask a question if I may, since now you got these rates.
Mm-hmm.
So K is the number of local steps, right? And R is the number of communication rounds, right?
Yes.
Mm-hmm. Capital M is the number of machines and so on and so forth.
Yes.
So one question here. So do I read this correctly? That if you work with the full gradients, the second term is not there because sigma is 0, and you recover the same rate as you would get without any local steps, right? So that's what you said, right?
Yes. Yes.
Even so, what about the constants? Will the constants be good or kind of reasonable that you get there?
The constants will be reasonable for this part, which is mostly because in some sense that this algorithm will reduce to this mini batch cases if we take a sufficiently small client learning rate. Because in this case, we have to set this eta server to be sufficiently large, and we only tune this eta client times eta server. And eta clients just has to be sufficiently small. This is more like a sanity check theorem to show that this will reduce to the centralized mirror descent if we almost don't take any client step, but just evaluate the gradients at the same state over and over again.
Yeah, so this is a result of the type of the classical type, of course, with the regularizer and so on, but of the classical type, which shows that local steps do not really help, that they only make things worse, and you pay for it with the second term, right?
Yes.
Do you also have some results under some similarity, data similarity condition where these local steps do help?
We don't have this because as we said that you need just sufficient small client learning rate. In some sense that if this eta client learning is infinitesimal, then it's just the mini batch. Mm-hmm. So there's not such assumption. So this theorem is somewhat sanity check theorem, and the main theorem will be shown later.
Mm-hmm. Okay. Mm-hmm. Okay, thank you.
Okay, no problem. The second theorem is only holds for Federated dual averaging. We assume that you can have a larger client learning rate, but unit server learning rate. This is more akin to the classic local SGD setting or the classic Federated dual averaging setting where you only average the primal states. We only average the client states during the synchronization stage. So this the result looks as follows. If you do not fix this client learning rate, then you have this bound. But you can find the appropriate eta client learning rate to optimize this bound. This bound requires a gradient bound, a uniform norm bound of the gradient, which is kind of reasonable if the domain psi is compact and this gradient is bounded. But we will see that how this gradient bound assumptions can be relaxed for the next part of the theorem. So if you look at this one, it has a faster convergence because you treat each local step as a step, whereas in the previous theorem, you most likely treat each server round step as a step. So this one shows the usefulness of client step. The third
question, sorry to interrupt.
Yes.
So unmute Edward.
Okay. Hello. So I
Yes.
have a question about the theorem 1. So
yes.
you mentioned that. Okay. So imagine that. So you mentioned that it's important that the step size, client step size, is sufficiently small, and
yes.
So am I right that you you handle the client drifts like in the scaffold, or you're just assuming that the second term dominates the term that depends on the local loss functions heterogeneity, like in local SGD?
This is mostly because, okay, so this is a simplified theorem. So if you want to look at the complete part of this theorem, please look at the paper. And the question is that, as you said, that all the remaining terms can be dominated by this first two terms if you take this client learner rate to be sufficiently small. So this is quite akin to the analysis of the scaffold or the other work that's considered sufficiently small client learner rates.
Okay, thanks. But so I mean that if sigma is 0, then there should be. So I'm trying to ask what? Okay, another question. What is what would the algorithm be if we plug constant regularizer?
Sorry, what do you mean by a constant regularizers?
So no regularization, no composite term.
Okay, no composite term. Okay. If there's no composite term, that's reduced to the Federated averaging.
Okay, then it means that it should be some terms that depends on heterogeneity, like in for local SGD, because we know that scaffold. So we know that local SGD suffers from this client drifts, and since this algorithm in a special case when the composite term is trivial, this algorithm recovers local SGD. It also has to suffer from this client drifts as well.
Okay, I understand your question. It's not like the local SGD in the classic sense, because in classic sense, a local SGD, the eta server has to be 1, and you are just simply averaging at the end of this round. But here we are taking this eta client to be sufficiently small and the eta has to be sufficiently large. But the eta client times eta server are at the right level. So if you consider the extreme case that eta client is somewhat 0 and eta server times eta client is at the right level, then it just reduces to the mini batch cases. And that algorithm will not suffer from the heterogeneity. Or another interpretation of that is that although there's there might be a heterogeneity term that related to the eta client, but since we can send eta client to be sufficiently small, this term will be handled by the remaining parts of this problem. But this is slightly different from like the other lower bound results for the local SGD. If you take eta server to be 1, then you definitely have to suffer from heterogeneity drift. But since we take this, because of this additional flexibilities, you can take this eta client to be small and eta server to be large to handle the heterogeneity. But this is not actually the case that people usually did for the Federated averaging. And we can say that this result does not have too much empirical implications because this term is usually the main issue of the problem. Does it answer your question?
Yeah, thank you a lot for the explanation.
Yes, feel free to send me an email if you are interested in the more detail of this part.
Okay, thanks.
Okay. I think we were at this slide where we show that the convergence of the Federated dual averaging in the unit server learner rates. So this one, The result looks as following. This matches the stage bound on the smooth unconstrained federated averaging. And so here's the results. Compared with the previous bound, we have faster convergence in terms of deterministic part because we can show that each client step has some usefulness. So consider the previous theorem is like you just query the gradient at almost same point and for quite a long time. For this result, it's like you have a you treat each client step as like a global step, and you compare with that mini batch with more steps but fewer batch. These results are, I think it should be quite familiar to the audience. If you are familiar with the stage Eckler 19 bound on the first analysis of OSGD, and here's the result. We are going to show a slightly more stronger result if we further assume that F is quadratic and heterogeneity is bounded. And the result looks as follows. Note that we only assume that F is quadratic. We don't assume anything else like the special shape of the psi. We can still like psi to be R1 norm, which will recover lasso, or we can take it to be a nuclear norm to recover the matrix estimations. And we don't assume anything else on the, yeah, that's it. Sorry. And the theorem looks as follows. In addition to assume one, we have to assume that the heterogeneity is bounded and F is quadratic. Then we have the following rate. After optimizing this eta client, again, we have to take eta server to be 1, which is more akin to the classic federated averaging setting. Again, we have this faster convergence rate, but this overhead due to the infrequent communication does not necessarily depend on the gradient bound because we no longer assume the gradient bound. And it has two terms. One is on the variance of the term and one the heterogeneity terms. I think this is exactly what constants are looking for, which is the case if you take this client learner rate to be larger. And this bound matches the best known bound on the smooth unconstrained federated averaging by Keld and Woodworth from AS-Data and Europe. So here's a quick comparison of the results. For fat mirror descent fat dual averaging in a small client learner rate regime, we have this theorem 1. The main issue here is that the convergence is slow because of the first term, because you only treat each round as a convergence round. On the other hand, we can show that fat dual averaging can achieve better results, potentially better results, if either the gradient is relatively bounded. Sorry, if the gradient is relatively bounded by the first term, or this variance and heterogeneity is dominated by the first term. Any questions on the theoretical parts of this result? I will go into the proof sketch very briefly, since we don't have much time now. Okay, so we are going to quickly go through the proof of this proof sketch of federated dual averaging. This proof sketch will cover the last two theorems on the federated dual averaging with unit server learning rate. So the main observation here is that the average dual state, if you consider this dual state where you average all the clients, this term is almost doing a centralized dual averaging of this form. So ideally, you want to evaluate this as the primal mirror of the ZRK. But instead, because you are doing a local version of the dual averaging, you can only evaluate at this client version. So we'll say that this one has a reduced variance, but biased, but it's a biased classic gradient hierarchy. This key observation enables the following lemma, where we can show that this convergence of this average dual state, which we call this shadow sequence. And this follows, the framework is similar to the so-called perturbed iterate analysis, which also appears on the previous analysis on the fat averaging. But we extend this to the dual states. And instead of measuring the primal difference, we have to measure the dual difference here. And you also have to consider the slightly different states for the point to evaluate. And the second step will be to bound this term. So if you look at this term corresponds to the stability characteristics of the ZRK. It's like you consider you run dual averaging from same initialization, but for a few different instances. Since each instance suffers from some noise, you can see that this will deviate from the mean after a few steps. And we have to show that this one does not grow too fast as you run the algorithm. For the Federated averaging, the benefit is that because of convexity, when you run gradient descent or stochastic gradient descent on this, you are almost pointing to the same direction. So this stability term cannot grow too large during the algorithm. But for our algorithm, we need slightly more stronger assumption, say quadratics. We guess that it's possible to even relax the assumption further, but we don't see an immediate way to reduce these assumptions, because in our analysis, this norm can be quite general. So the analysis of stability term is not immediate, and there's no result on quantifying the stability of dual averaging in the existing literature. We'll quickly go through the experiment part of this work. We will evaluate actually 4 algorithms. The first 2 are the Federated dual averaging and Federated mirror descent. You can consider this Federated mirror descent as most likely as a baseline, because it's in most akin to the standard Federated averaging. But you just simply replace the gradient step with the proximal step. Federated dual averaging is our main algorithm. On the other hand, we also consider 2 more algorithms which are slightly more, which are less principled. The idea here is that you can reduce client's proximal step, but only perform several proximal steps. This is mostly for ablation study purpose. So the algorithm looks as follows. Recall that this is a Federated mirror descent. We can craft a OSP only server proximal version of the Federated mirror descent by replacing the client's proximal steps with something that does not involve this psi, but you only do this psi in the server step. You can consider that when you run projected gradient descent, the client just do whatever they want, ignoring the constraint, but it's projected back to the constraints only at the server. So this one is completely unprincipled, but we just study this and implement this to see that what is the potential way to further simplify the oracle complexities for this part. Note that if we take this discontinuity function to be the norm squared, then this term is nothing but the gradient descent step, which is almost doing a Federated averaging at the client step, but you only do a proximal step at the server. We can do the same thing for the Federated dual averaging OSP version. We will evaluate on 4 different experiments. The first experiment is on the Federated lasso for a synthetic data set. The reason we use a synthetic data set is that we can specify the ground truth, so we can compare our result with the known ground truth. The way we generate the data set is that we first fix a known ground truth W star, and then we generate a bunch of different clusters of X to simulate the heterogeneity among clients. And the problem just looks as follows. So you minimize this lasso problem subject to a L1 constraint. And since we know the ground truth, we can compare the estimated sparsity with the real sparsity. So we can evaluate F1 score, precision, recall, and we can also record density, where the density is just the number of non-zero elements over all the elements here. Here's the experimental result. What we can observe is that the Federated mirror descent classes are somewhat less efficient in recovering the sparsity. If you run this if you run this algorithm for sufficient number of rounds, then you can eventually show that it will converge, but that will take a quite long time to converge, which is kind of because of what we have just observed before, the incommutability of proximal steps and the averaging steps. Obviously, the Federated dual averaging, our mean algorithm, can almost immediately recover the right sparsity patterns. And this OSP version, surprisingly, can also do a quite good job. but it's less efficient than the Federated dual averaging. But this reveals a possibility is that for certain class of problem, if the Oracle is quite expensive, like 10 times more expensive, then you might want to consider Federated dual averaging, the OSP version of this. It's a green line. But for this L1 problem, it's not that obvious because the L1 proximal Oracle is very cheap. We also tested different settings like different the sparse data sets, even sparse data set or more distributed data sets, and the trend are almost the same. As we can see that for this more distributed data set where the client is increased from the 64 to 256, the mirror descent gets worse because its convergence is much slower, but Federated dual averaging can still converge in less than 100 rounds. Another experiment is on the low rank matrix estimation, where the goal is to optimize this one. Sorry, so we still work on synthetic data set. We first generated a low rank ground truth W star and generate a bunch of X and epsilon point to simulate the synthetic data sets. The goal is to optimize this objective function subject to, not subject to, but with additive nuclear norm regularizations here. Recall that nuclear norm corresponds to the sum of singular values. And the reason that this nuclear norm is feasible, is reasonable, is because you can, it's because the proximal step of the nuclear norm reduced to the singular value thresholding. There are other more efficient way to do this, but we mostly focus on this soft singular value thresholding for simplicity, because this is Oracle we are starting for this work. The metric here, we evaluate the training loss, validation, MSE, and recover rank, and recover error in Frobenius norm. And we also compute the optimum, which can be obtained by solving this with a deterministic solver. And as you can see, that Federated dual averaging still leads all the baselines. For example, this orange and red line correspond to the simple fix of the Federated averaging, barely works. But the Federated dual averaging can work quite fast. This green line, the OSP version, the less principled version, can sometimes work, but it's not obvious because you can see the recovery error is bad. But it does do a good job in recovering the right rank. We also tested on other different specifications of the data sets. In the third experiment, we tested the sparse logistic regression on the fMRI data set. The goal is image classification, like a binary image recognition task. You give a fMRI scan to a patient, and when you give stimulus to those patients, it's one of two images, and you want to infer that whether this corresponds to the first image or second image based on the fMRI data scans. This data set is by HexBy, where there are 6 subjects, 11 to 12 sessions per subject. We treat each state client to present the data of a session, and therefore there are 59 training clients in total. And we run L1 regularization logistic regression. The reason we want to run a sparse logistic regression is that we want to recover the specific area that corresponds to a specific area of the brain, which corresponds to a certain task or functions. And this would be useful for the researchers to identify the functional of the brains. And we evaluate the following densities. As we can see that this centralized corresponds to you just run L1 regularization task with everything pooled, with all the training data pooled, which is more like centralized setting. And this local baseline corresponds to just running on one client, which is obviously bad. But if we are not allowed to share data, but we still want to run this job, then the brown one is the only thing we can do. This is of particular interest if that in certain application of biomedical tasks, due to the regulations, you might not be able to share the data with others. But running this in the cross-cellular settings might be useful. As you can see that this blue line corresponds to a validation accuracy, a high validation accuracy, and low density, which is exactly the thing we want to recover. The other things are either too dense or too less accurate. We also run a few other experiments. This is on the constraint FL, where we optimize our objective function subject to a norm ball constraint. We tried L1 normal constraints, L2 normal constraint, and also L1 constraints on non-convex objectives. This is more like an experimental experiment because we don't have any guarantees for the non-convex objectives. This is actually very hard because for non-convex proximal green descent, you have to introduce a sufficient amount of assumptions to make it work. And we just simply run this as it is to see that how it behaves. And surprisingly, the Federated still behaves well. And you cannot see the green line here because that one basically does not work. But if you look at the other ones, the L2 constraint logistic regressions, this green line still makes a reasonable progress. It has a high training accuracy and high test accuracy for some reason, but the training loss is bad. But the take-home message that Federated these are the baselines in all the settings. Okay, that's end of the talk. Sorry for overflowing for 3 minutes. I'm happy to take questions either online or via the email. And our paper is here, archived a few weeks ago. Thanks.
Thanks a lot, Honglin, for this wonderful work. If there's any questions, anyone, I think Mary, you can unmute everybody and people can ask in this standard way. Just yeah.
Okay, so now everyone
without
can
getting
unmute themselves.
So while people are thinking, let me ask a question. So you mentioned at the very beginning that this regularization could have something to do with personalization. Did you have any concrete ideas about this?
Actually, we are working on this. And I think there's some fundamental challenges because it corresponds more like alternative projection. If you treat each constraint, if you treat each composite as a personalized constraint. And this is actually much harder than either this regularizer setting or the simple smooth Federated averaging setting. We are still working on this, but we just propose this question as the most general cases.
Yeah, but I was also thinking not whether you could analyze this, but how could you model personalization using this formulation? So what kind of personalization could you model with this? Because one thing you can say, obviously, is we just say that your W belongs to some set, but why would somebody want that? So why would you call that personalization? So that is a constraint, yes. But personalization may mean something else. It may mean, for instance, that I am a device and I have data mostly of street photos, and I want my model to do well for these street photos, and I don't care about data having to do with, I don't know, boxes of all kinds, because I just don't take those kinds of photos. I want my model to be personally good for my own data that I'm going to see. And this may be difficult to model by introducing a regularizer of this type, right? So
yeah,
what kind of personalization, useful personalization strategies could be encoded this way?
Yes, I think the example you just described are more like a multitask learning. And it's not that easy to be modeled by the constraint or regularizers. Yes. The personalization I'm looking for is more, it's more outside, it's more like from outside the machine learning. It's more like a pure optimization. Where the goal is that each client has some constraints because they want to spend some money to buy something, but they do have some personalization constraint, and they have a budget constraint or other kind of constraint. I call this personalization. It's perhaps not the personalization in the scenarios you described, but I think it can be useful for certain optimization tasks. And yeah, so that's why we call it personalization. And of course, I think we can even generalize this problem to the multitask setting where, for example, each client has a subset of the parameters, and they want to learn the representation jointly, but have a different personalization like layer on the top of representation. But that is obvious outside the scope of this work, but this is a good question, and I'm happy to explore this in the future.
Thank you. Anybody else wants to ask a question? So you can unmute yourselves now and simply just ask. Okay, still people not unmuting. So I'm asking another one. So you have this uniform bound sigma on the variance for the stochastic gradients. Do you think your approach could be generalized to some more complicated and more practical bounds? So
yes.
something where you would have so something that would, let's say, be satisfied for mini batching on each device, because this bound is not satisfied for mini batching unless the regularizer forces everything to be in some compact set.
Mm-hmm.
Is that approach extendable?
Yes, I think it's a good question. I think an obvious way to generalize this bound is to only specify the variance bound at the optimal point. But this obviously leads to a worse bound. But I would say that the most of analysis will be doable without too much change, because I think this part are pretty much akin to the analysis of Federated averaging. So I think there are some work on Federated averaging that assume that kind of bound. So I assume that we can almost do the same thing. But that would definitely complicate analysis by a little bit. And it is perhaps not exactly useful, because in a heterogeneous setting, you don't, this one will have both the heterogeneity and the variance if you only specify W star. So this is one potential choice. Another potential choice to consider the ERM setting, where each client has a fixed amount of data samples, and you want to run like empirical risk minimization on top of empirical risk minimization. I think this is mostly doable, but we would expect more algorithm more like SVRG or other variance reduction technique to reduce the variance inside each client. And that will entail some combination of the dual averaging and the variance reduction technique. It can be doable. I'm not sure because I never tried this, but it sounds like a promising direction. And I think it's also a promising direction even for unconstrained settings to reduce the variance inside the,
In the unconstrained setting, this was already done, but I do not know, because I didn't think about this, whether in this setting it's possible.
Yes.
Okay, good. Thank you a lot.
No problem. You're welcome.
Last chance to ask some questions. Okay, so I think this is it. Thanks a lot for the very nice talk and for introducing us to your recent results. Good luck with your future research, and tune in next time. We're going to skip next week because of NeurIPS, but then there is one more talk, and then we'll have a longer break and restart at some point in January. Okay, thank you. Bye-bye.
Thank you, Honglin.
Thank you a lot. Goodbye.
Thank you.